Yeah, problem sets and then syllabus. Good on you.
A little bit here and there. The modesty of they're tailing behind you, Daddy.
So did everyone get a syllabus?
Nope.
And did everyone get the problem sets there? Just one, I guess. Can you guys hear me? Okay, great. All right, well, here's the problem set. All right, why don't we get started? Make sure you picked up the. Okay, so my name is Raj, and I guess the purpose of these sessions are to allow you to feel comfortable with biostatistics when you read through medical journals like the New England Journal, Lancet, those types of things, and to be comfortable with studies, and also to be able to use biostats in your own research. And these sets of review sessions will prepare you for the competency exam, which will be 2 weeks from this weekend. And if you pass out of that, then you don't need to take the January course. And I don't mean to tell you that just by coming here and not not actively getting involved, that it's going to be easy to pass this test. I mean, in past years, it's been very difficult to pass out of the exam. But I can tell you that everything that we're going to cover here and more, I mean, we're covering more than what's going to be on the exam. And if you do the problem sets and you understand them, you'll have no problems passing the competency exam. So if you guys just put in a little effort now for the next 2 weeks or so, you'll save yourself a lot of time in January. And the problem sets that I give will be, except for the first one is the longest one, but the problem sets that I give will be a lot more easy and less time consuming than the ones you'd have to take in January. Okay? But it's not going to be that easy, it's not going to be trivial. You will have to learn it, okay? So the topics that I'm going to cover, essentially we're going to go over 4 2 to 2.5 hour sessions over these 2 weekends. I'll make sure I end early tomorrow so you guys can go to the cruise, right? Yeah. Yeah, I'm going to pass out the answer keys. So actually, what I would prefer is, if possible, you guys finish the first problem set by tomorrow, and then I'll pass out the solution. Just because if you get this stuff early on, then tomorrow's lecture will make so much more sense. So that's one thing I'll ask you, is finish the first problem set by tomorrow so that you're set for the next couple of lectures, okay? So we're going to have 3 or 4 problem sets, and I'll have office hours over the week. Like I said, here's the first problem set, and I'm going to ask you to do this one just in this one day so that you guys are set for the next few lectures. And today what we're going to talk about is we're just going to go over a brief introduction, and then we're going to talk about probability. We're going to talk about sort of probability theories like Baies theory, and then how that's applied to diagnostic tests with sensitivity, specificity, and all those things. Then we're going to talk about general statistics like normal distributions, binomial distributions, and then end off with one sample comparisons. Okay? And then we'll be set. Yes?
So for for the subsequent sections, do you actually want us here? Is it okay if we watch over the internet? I guess we can tape for that.
Yeah.
Matter to you, or?
I would prefer that you guys were here. I think it's much easier for you to see on the board. I don't know how this videotaping is going to work. Theoretically, it's going on right now through remote sensing, but I don't know what it's going to look like on the board. So so I don't know. You'll have to do it at your own risk, sort of, because I don't know what the quality will be like. Okay. And you won't be able to check tonight what the quality is like, because today's lecture won't be up until Monday or Tuesday of next week. Okay, so let's get started. Pretty much my style is to do everything by the board, because that forces you to write everything down, and then you guys learn it. So just in general, it's going to be very important for you guys to know biostatistics. The Human Genome Project has and these whole DNA chips has forced biology into the biostatistics realm. Everyone is using it now. You have to know what analysis of variance is. You have to know what survival analysis is, just essentially because of the Human Genome Project and all its data. So really what I want to do now is just jump into the statistics, and then at the last lecture we'll talk about more about clinical trials and how to design experiments after you have sort of the background in statistics. And just by a show of hands, I'm curious, how many of you have already taken a stats course? Okay, so a good number of you. So a good number of you have seen this. So this will be a good review. And we'll be all set. So the first thing I want to talk about is probability. And stop me at any point if you have questions. Okay. So first things first, you always have to, the hardest thing about statistics is getting the notation down. And with probability, there's also a notation that you have to know. First thing you need to know, well, first of all, the probability of anything always lies in between what values? 0 and 1, exactly. And the first notation that you should be familiar with is this, which is essentially means the probability of either A or B. Okay. And we can always visualize probabilities with, areas. And if this is A and this is B, the union of A and B, their areas will be like this. Okay? Or if A and B, do you guys know the term of when these two areas don't intersect? What is that called, A and B? They're mutually exclusive. Exactly. And they don't have to be mutually exclusive. You can also have A and B with some overlap, which means they're not mutually exclusive. In other words, they can both occur at the same time. Mutually exclusive means that they cannot occur at the same time. These are not mutually exclusive, and what would be the area of A and B? A or B, sorry? It would just be the whole area here. Okay? The other notation is A intersect B, which is essentially just means the probability of A and B, the probability that they occur simultaneously. In the first case, what would that probability be? 0, because they don't intersect. They never occur simultaneously in this first diagram. In the second diagram, that would just be, well, I'll redraw it, but that would just be the intersection area. Okay? So not so bad. Essentially, there are 3 rules of probability that you have to remember to understand what we're going to be going through. The first rule is essentially just a definition. It's the probability of A given B. I'll write it out. The probability of A given B is equal to, so this vertical line means given, is equal to the probability of A and B divided by the probability of B. That's the first rule that you have to remember. And let's sort of talk about it to make it sensical. This makes sort of a lot of sense if you look at it from this perspective. So let's say this is the universe. Okay, this area here. And the probability of something like B occurring is 1/3. Okay, let's say that. And let's look at another variable, A. And let's say the probability of A occurring is 5/6, where it starts from 1/6 and goes all the way to 1. Okay? Now, just intuitively, what would you guys say is the probability of A given B? So just if we work out those words, the probability of A given B, so we're given that B is true. So we're only looking at this area now. This is our new universe. And what's the probability of A within this area? It's 1/2. Exactly. So the probability of A given B is 1/2. Okay. Just the probability of A within this area. Well, let's see if our definition holds true. What is the probability of A and B? What's the probability of both A and B occurring simultaneously? It's just this entire area relative to the whole area. So it's 1/3 minus 1/6 is 1/6, right? And what's the probability of B? It's just the initial area, 1/3. Okay? And that works out. So essentially what you're doing in your head is exactly what this diagram is showing. The probability of A given B is the probability of A within the area B. Okay? That's all it means. One thing that we can learn from this, actually, is the following. We can solve for probability of A and B, right? So the probability of A and B, if we just cross multiply, is the probability of A given B times the probability of B, right? But is there any difference? What if we were to switch the orders? What if we were to say probability of B and A? Is there any difference between these two? No. And so we could rewrite this as the probability of B given A times the probability of A. Does that work? Let's check with our example. What's the probability of B given A? So again, we look at the area A. Given A, whose area is 5/6, what is the probability of B, whose area is 1/6, right? It's going to be 1/5. And what's the probability of A? It's 5/6. So that comes out to be 1/6, which is what we had come up with before. Okay? Does this make sense so far? So first rule, you should remember probability of A given B is just the probability of A and B divided by the probability of B. The next rule, if I erase this, the second rule that you should remember is independence. And so the rule here is that the probability of A and B equals this probability of A times the probability of B if and only if A and B are independent. So the only way you can separate these probabilities into a product is if the two are independent of one another. Are A and B independent here in this example? Let's check it out. What is the probability of A and B in this example? It's just this area in between. So that's a sixth, right? And what's the probability of A alone? It's 5/6. And B is 1/3. So no, they're not independent. Okay? What does it mean to be independent? Or actually, what would you see if they were independent, the variables A and B? Exactly. So knowledge of one doesn't tell you anything about knowledge of another. Or another way of saying that is, regardless of whether B is true or not, the probability of A stays the same, right? So regardless of whether B is true, so if B is true, the probability of A stays the same whether it's true or not true. That's another way of saying it. The probability of A doesn't change regardless of B.
Is it vice versa?
It's absolutely vice versa. So, in other words, the probability of A given B is the same as the probability of A if B were not true.
Don't put A equals the probability of just A.
Equals the probability of A. Absolutely. Good. This is true only if A and B are independent. Okay. And then the last one is a little bit more obvious of a rule, but I just bring it up because we'll need it to derive Baies' theorem. And that's just the following. The probability of A in general is equal to the probability of A and B plus the probability of A and not B. Right? So in other words, you're just breaking down this area here for the probability of A into two separate areas. The probability of A where B is true, and the probability of A where B is not true. And then you're just adding them together. Okay? To get the total probability of A. Why am I bringing these three rules up? Because now we're going to prove Bayes' theorem. So are there any questions on these three rules? Okay. So we'll now move to Bayes' theorem. And what Bayes' theorem says is the following. It says the probability of A given B is something really horrendous. But we'll come to it in the end. First thing I want to do is just recopy what we said here. Right? The probability of A given B, right? If we set these two equal to one another, right? If we were to set those two equal together, let me see what we would get. So probability of A given B times the probability of B is equal to the probability of B given A times the probability of A. So now let's solve for this term here. And what we end up with is that the probability of A given B is just equal to the probability of B given A times the probability of A over the probability of B. So we used rule number 1 so far. Now, let's just use rule number 3 for this term. Okay? And what we get is, becomes, the numerator stays the same, but the denominator can be broken up into two parts now. It's just the probability of B and A plus the probability of B and not A. That's just the total probability B. Right? And then the final step is just to convert these back using this initial definition here in rule 1. Where what we're doing is we're just converting back to the givens. What's the probability of B and A if we go back to the given? It's just going to be the probability of B given A times the probability of A plus the probability of B given not A times the probability of not A. And then the numerator stays the same. And that's what Bayes' theorem says. Just with 3 different steps, he gets his name on a theory. Pretty simple. The reason why I'm going through this is not because you necessarily need to know the derivation. It's just because I want you to know that Bayes' theorem comes from just the simple rules of probability. Essentially, they're just coming from these definitions. This and this. It's like all notation.
Question.
Yes.
Are there previous years' competency exams that we can look at?
Nope. There are no previous year's competency exams. But these problem sets are reflective of the competency exams. Yes.
Why is this useful?
That's what I'm going to get to right now. Why am I going through this? What does it have anything to do with medicine? It's a great question. And where it comes into play is when we look at things like sensitivity, specificity, positive predictive value of these tests for diseases, right? So that's what we're really interested in. So let's start talking about that. Let's start talking about diagnostic tests. And that's where Bayes' theorem is really important. So let's just define the notation first of all. D plus means the number of patients with a disease, and D minus are those without the disease. Okay? T plus are the number of patients who test positive for the disease. And T minus are those who test negative. All right? So what we can do is we can construct a 2-by-2 table. Okay. And let's do this with an example. Let's do this with the example where the disease is having a heart attack, a myocardial infarction. Okay. And there was a recent study where patients would come into the emergency room with chest pain. Okay. And of 230 patients who came in with chest pain and were shown to be in a heart attack, 215 were positive for the cardiac enzyme marker creatinine kinase, CK. Okay. So they tested positive for the cardiac marker, and 15 tested negative. Oh, sorry. It was 220, sorry. And only 5 tested negative. Then, they saw another additional 130 patients with chest pain who did not have a heart attack, it was determined. Of those, 114 tested negative for the cardiac enzyme, and 16 tested positive. And so the total number of patients was just 350 that they looked at. So what sort of information can we gather from this data? Well, first of all, if we label these with letters A, B, C, and D, that's the notation that's usually used. And whenever you construct these tables, you always put the disease in the columns and the tests along the rows. Okay? That's the convention that's used. Okay. Well, given this information, you can sort of get a sense of how good this test is for looking at this disease, looking at heart attacks. What's the sensitivity of the test defined as? Okay, so you guys had your path lecture on this. All right, but it's defined in statistics term is the probability of testing positive given that you have the disease, right? So now you understand why I was doing all this probability, right? Why I was going through all this probability notation. It's for this. So the sensitivity is defined as the probability of testing positive given that you have the disease. So if you were to put it in terms of this table, the letters A, B, C, and D, what would it be equal to? It would be A, the number of true positives, the number of people that tested positive. These are called the true positives, right? Divided by A plus C, the total number of people with the disease, right? So what does C represent in this table? It's the false negatives. Exactly. And so this is equal to A over A plus C. And that will be 215 over 220 in this example.
How does it fit when you say just positive plus just A? I mean, it makes sense the way it's mentioned.
Because you're looking at, see, that's why it's the notation given that you have the disease. So it's the probability of testing positive given that you're already known to have the disease. So you're only looking at that column. All right. What about the specificity? What is that defined as? Exactly. It's the probability of testing negative given that you don't have the disease. Okay. And what will that be equal to? D are the true negatives, right? And B, if you look at it, are the false positives. See, now we're only interested in this column. And so, it'll be D over B plus D, which is 114 over 130. So what you see is that how good the sensitivity is depends on the false negative rate, C. And how good the specificity is depends on the false positive rate, D. Okay? What is the advantage of sensitivity and specificity? What do we know about it?
What do you mean?
I guess it's one of those things, can you read my mind, right? Let me explain. Let me erase this part right here, and I'll come back to this. But when I think of sensitivity and specificity in these types of tests, one way to look at it is the following, just graphically. You have two populations, one without the disease and one with the disease. And you run your test, right? And just say your test is the CK level, creatinine kinase level. And somewhere you say, okay, let's make a cutoff. And everyone to the right tests positive, and everyone to the left tests negative, right? And so if I were to color in this area right here, that's underneath this curve, what would that area represent? It would be those, yeah, exactly. It would be those people that test positive but don't have the disease. That would be the false positive rate. And what about this area right here? Well, those are the people who test negative but do have the disease, and that's the false negative rate. Okay? And so what happens if I were to shift this cutoff to the right? You would reduce this, but the number of false negatives would go up, right? So it's a push and pull with these sort of tests. Depending on what your cutoff is, you'll decrease the false positive rate or increase the false negative rate. So which one of those did that affect? The false positives affect the specificity, and the false negatives affect the sensitivity. Okay? So depending on what your cutoff is for your test, you're going to increase either the sensitivity, you'll maybe say increase the sensitivity, but at the same point you'll be decreasing the specificity. Unless you were in an ideal world where you had two separate populations and you knew exactly where your cutoff were. But that never really happens. There are some tests that are pretty good at it, like measuring serum HCG levels for pregnancy. But otherwise, it's really tough to get a very accurate test. Okay? Now, the point I was going to get at now, in terms of reading my mind, is what's good about sensitivity and specificity? So what if, and what I was getting at here was, what if I were to increase the prevalence of the disease? So this area, the shape of the curve stayed the same, but just the prevalence became higher. Okay? Would that change the sensitivity or specificity? Remember what specificity is, right? It's going to be this area here, the false positive area, well, it's going to be dependent on this false positive area. Sorry. Relative to what? What are we comparing this false positive area relative to when we're looking at specificity? We're looking at all the disease. We're looking at the people with the negatives. So we're only looking at one curve. That's the point I'm trying to make. When we're looking at specificity, we're looking at those people who test negative given that they don't have the disease. So if we really wanted to draw it in, let me get the different color here. If we really wanted to draw it in, what the specificity was on this graph, it would be this probability right here. Right? It's all dependent on just one curve. Okay? So changing this curve won't have an influence on the specificity. Okay? Specificity is this fraction over the total fraction here. It's whatever's in pink divided by the total. Same thing you could argue with the sensitivity. The sensitivity is this area here. It's the true positives. It's this whole area divided by all of the people with the disease. Regardless of whether you increase the area of the curve, the proportions are going to be the same. And so the only point I'm trying to make with this is that sensitivity and specificity are independent of the disease prevalence. Can anyone define for me what prevalence is?
Can I
You have a question?
first?
Sure.
Because, I mean, I see what you're doing here and it makes sense, except that if you're talking about proportions of people and the population size stays the same, aren't you implicitly reducing the size of one as you increase the size of the other? I mean, doesn't the total area under both of those curves?
Absolutely. Yeah, I just didn't draw that in. But you're right. If the total population stayed the same and you increased one and decreased the other, would you be affecting sensitivity or specificity?
Be affecting both.
Why?
Because the size of your let's say your true negative curve is going down.
No, but see, the thing is the specificity is this area divided by the total area. So even though, so by reducing the size, the shape of the curve stays the same, and so you don't affect it.
In your first explanation, your assumption was that the proportion of B minus B plus, the total number didn't change. B minus plus B plus was equal.
Yeah, that's what he's saying. The total population is the same.
Yeah. If B plus just increased with no change to B minus, then your specificity would change.
Why?
Well, I mean, for example, if you had your, true negatives over true negatives or false positives. For specificity, true negative over true negative or false positive. So if false positive isn't changing, assuming that B minus isn't changing, then B
Here.
plus.
Right. Let me just explain this. So here's your D minus, just say, and here's your cutoff value, right? And so this is going to be your true negatives, and these are going to be your false positives. Regardless of what the size of this curve is, as long as the shape stays the same, regardless of what the number of people it represents, this proportion of true negatives over true negatives plus false positives is going to be the same. Okay? It's going to be the same. Yep.
This is only true if you set your cutoff in terms of standard deviation.
What do you
not
mean?
if you set it as a number.
Yeah, that's my point. Exactly.
Why do you say that?
Well, because, unless it's a property of normal curves that I don't understand, if you just increase the height of the curve and you don't adjust your cutoff based on standard deviation instead of just on a pure number, then you are going to change.
I agree completely. It's all based on the number of standard deviations. It's not based on there's no fixed number. I agree with that. Yeah.
So just to clarify, if you do increase the size of this curve, the curve we're drawing here is not really a curve related to the number of people in the healthy population that tested at a certain level. What we're really dealing with is an underlying probability distribution, which is completely independent of the number of people in the healthy population.
So yeah,
Say-
theoretically, the area under the curve should always be 1. Is that what you're saying?
Well, so what I'm saying is that when you're thinking about the curve changing shape, rising or lowering, it's true that your sensitivity and specificity are going to change. But what you're doing is not just changing the number of people that are healthy or whatever. You're doing is changing the property, how the test responds to a healthy person. That's what you're changing. So,
But my point is you're changing both at the same time in the real population if you ever tested the cutoff.
Right. So I
Like
adjust
age
the
goes from
standard
0.3%.
Yeah, you'd have to adjust. Absolutely, you'd have to adjust both because you're assuming maybe they'll have the same total population, and even if you change the numbers in each group, what you're assuming is that the mean of each group and the standard deviation of each group will stay the same. Right? That's what we're assuming. Okay. Really, all you had to get out from that was that the sensitivity and specificity are independent of the prevalence. That's all I wanted to say. And that is good. And what I was just trying to illustrate from this graph is that the specificity is completely dependent on just one curve, the d-minus curve, right? And the sensitivity is just completely dependent on the d-plus curve. But when we look at the other two variables, positive predictive value, which is defined as what? What's positive predictive value defined as? Exactly, it's the probability of having the disease given that you test positive, which in this table would be equal to, now we're only looking at given that you test positive, so now we're looking at the rows. So we're looking at A, the probability of having the disease given that you test positive, A over A plus B. And in this case, it would be 215 over 231. Okay? And the negative predictive value would just be the probability of not having the disease given that you test negative. So now we're looking at this row. Okay. And that's going to be D over B plus D. Sorry, C plus D. C plus D. Right. And if you want to put numbers on that, that's just 114 over 119. Okay. The difference between positive predictive value, these predictive values versus sensitivity and specificity is one way to look at it visually is, let's just look at it. A is just a true positive number over the two positives plus the false positives. So when you look at these graphs over here, the true positives, if I were to draw this, the true positives are in blue, and the false positives are in this orangish color. You can see that they're both under different curves. The true positives is under the curve of those people with the disease. The orange color, the false positive, is under those without the disease. So now, when you play with prevalence, and you're changing one curve relative to the other, you are going to change the values of the positive predictive value and negative predictive value. Okay? So these two depend on prevalence of the disease in the population. So let's just quickly define prevalence. How would you define prevalence of a disease? Well, essentially all it is that at any given instant in time, it's the percentage of people in the population with the disease. So at any given time, it's the percentage of the population with the disease. And I'm distinguishing that from incidence. How is incidence different?
number of people who are dying, or number of people who contract that disease in a given day.
Yeah, so it's essentially, incidence is a frequency. the number of new cases of the disease that develop over a given amount of time. So it's the new cases that develop, just say, over a given amount of time. Okay? So whereas there might be 2 million people in the United States with HIV right now, which would be the prevalence, another, I don't know, I'm making this up, another 50,000 will develop the disease in the next year. Okay? That's the incidence. Does that make sense? Okay, because I want to go over an example. I think it's very important for you to do examples, for us to do examples in class, just to nail down the concepts. Oh, and why did I bring up Baies theory? Why did I bring up Baies theory? So we're not ready for the example yet. So the reason why I brought up Baies theory is to compare positive predictive value with, to derive out what positive predictive value is. So let me, does everyone have these? Can I erase this part? Thanks. Let's just derive positive predictive value. So positive predictive value, which according to the table we know is already equal to A over A plus B, okay, is defined to be the probability to have the disease given that you test positive. Okay? And if we use Bayes' theorem, we'll just flip everything around. I mean, we'll just use Bayes' theorem and say this is A, and this is, you know, we're using Bayes' theorem here, so this is A and this is B. So this is going to be equal to the probability of testing positive, given that you have the disease, times the probability of having the disease, right, over probability of the same thing, testing positive given that you have the disease, times the probability of having the disease, plus, just continuing on with the equation, the probability of testing positive given that you don't have the disease times the probability of not having the disease. And if we were to put this into words, what is this first probability? Probability of testing positive given that you have the disease. It's the sensitivity. And what's the probability of having the disease? Prevalence, right? And these two terms are just the same, so it's over the sensitivity times the prevalence plus, what is this term? The probability of testing positive without having the disease? So this is the false positive rate, right? And the false positive rate is just, you guys realize, is 1 minus the specificity, right? Because if you look at the specificity, it's D, the true negatives, over the true negatives plus the false positives. And this term here is just 1 minus that. So it's 1 minus the specificity times the probability of not having the disease, which is 1 minus the prevalence. Okay. Well, let's check out this derivation using these letters. The sensitivity we know is A over A plus C. And what is the prevalence equal to? The prevalence is just those people with the disease, the fraction, so it's A plus C over the total number of people, N. Okay. Now we'll look at the denominator. You get the same thing in the denominator. So it's A over A plus C times A plus C over N plus, what is 1 minus the specificity? Remember what the specificity is? It's just D over B plus D. So 1 minus that is B over B plus D. And what is 1 minus the prevalence? Right? If the prevalence is A plus C over N, 1 minus that is just going to be B plus D over N, right? Okay. So we get a lot of things crossing out here. These two cross out. These two cross out. These two cross out here. And what you're left with is A over N divided by A over N plus B over N. All the N's cancel out, and you're left with A over A plus B. That's what we had already defined positive predictive value to be. So Bayes' theorem works. If you had a doubt. What was that? So statisticians will say, use this equation to calculate a positive predictive value. Right? Just plug it into this equation and you'll get it out from the sensitivity and prevalence. What I'm going to tell you, the reason why I went through all this is to show you you can get the positive predictive value just from the table very easily. So now when we do this example, this next example, what I'm going to show you is using both methods, but the one with the table I think is the more valuable one because you'll get more information quicker. Yes. Did that answer your question?
Yeah.
Okay, yep.
Just want to make sure I understand. So in order to get positive predictive value or negative predictive value, you need or you could use, if you have the sensitivity and specificity, you also need to know some of the overall numbers, like what is the probability of having a disease in the population.
Yeah, all you need are those three: sensitivity, specificity, and prevalence in order to calculate the positive and negative predictive values. Absolutely. All right, let's do an example, because this is a bunch of equations and we want to apply it all. So, can I move this board up? All right. All right, let's do a quick example here. All right, so suppose that 90% of people with lung cancer and 30% without lung cancer are smokers. The prevalence of lung cancer in the population, just say, is 10%. We know it's not that high, but maybe we're looking at among people who are above 65 years. That's our population. So it could be 10% in that population. Questions are, what are the sensitivity, specificity, and positive predictive value? So why don't you take a few minutes to think about that, and then we'll go over just systematically how to do this. So Salil asks, what is the test? So what is the test in this question? Smoking. So if you are a smoker, you test positive. So it doesn't necessarily have to be a test, but it can also be a symptom. Okay? Or a habit, or what, whatever. All right, in the interest of time, let's start. So start by forming your 2x2 table in these types of questions with the disease in the columns, so those with lung cancer here and no lung cancer here. And those who do smoke here and no smoking there. Okay. And we know 90% of people with lung cancer are smokers. Right? So we'll say 90, just assume that there are 100 people here. 90% are smokers and 10 are not. Okay. And of those in the lung cancer group, 30% without lung cancer are smokers, and so that means 70 must be non-smokers. So that's how you would organize the table. What is your sensitivity? How would you calculate your sensitivity? Again, just to review, sensitivity is the probability of testing positive given that you have the disease. So what is that probability? Yeah, just 90 over 100. It's just the number of true positives over true positives plus false negative. And the specificity, the probability of testing negative given that you don't have the disease. And that's going to be 70%, right? Remember, that's just the true negatives over the true negatives plus the false positives. What about the positive predictive value? And then we know A, B, C, D, right? Why isn't the table right? What's wrong with the table? Doesn't take into account prevalence. What's the prevalence of the disease with this table? 50%, 100 and 100. How do we change that to get a prevalence of 10%? How about we multiply this by 9? Everything in that column by 9 to get 900. So that now 100 out of 1,000 people have the disease. This is 270. This is 630. How's that? Sorry, I'll try not to pace. Sure, she's getting annoyed. Because there's someone actually controlling the camera downstairs. So do you see that little trick, how you include prevalence in the table? You just multiply this column by whatever you need to get the right prevalence. Okay? So the total number of people are now 1,000 with the 10% prevalence of the disease. What would the positive predictive value be? Again, positive predictive value is the probability of having the disease given that you test positive, which is simply A over A plus B, and that's 90 over 90 plus 270. 90 over 360 is 25%, 0.25. Does that make sense? Now what you could have done is you could have plugged these values into Baies' theorem. Remember, the positive predictive value is the sensitivity times the prevalence, or the sensitivity times the prevalence, plus 1 minus the specificity over 1 minus the prevalence. Right? And that's just equal to the 0.9 times the 0.1 over the 0.9 times the 0.1 plus 1 minus the specificity. The specificity is 70%, so 1 minus that is 30%, times 1 minus the prevalence. The prevalence is 10%, so 1 minus that is 0.9. And what you see is you get